All the major tests that we have used so far to analyze the convergence or divergence of a series, such as the integral test, the ratio and root test, or even the comparison tests, were done on the assumption that the sequence associated to the series consisted of positive numbers, of positive terms, or at least eventually positive. In this class, we're going to look at what happens when that is not the case, and when in fact the series that we're dealing with will have infinitely many positive and infinitely many negative terms. Okay? In particular, we're going to look at one type of such series called, of course, the alternating series, which, as the picture suggests, are in fact swinging back and forth between positives and negatives. Generally speaking, series that have infinitely many positive and infinitely many negative terms have some really interesting properties, and so do alternating series. We're going to look at some of these properties in this class. There are other properties that may be associated to non-alternating series which also have the same property of having infinitely many positive and negative terms, but those will you will probably see in later courses. So let me tell you, first of all, let me start by telling you what the problem, what the issue is that is related to whether the series is eventually positive or not. Now, first of all, if we're looking at an eventually positive sequence, which is done in such a way that its series is convergent, it turns out that then the series is convergent to the same sum no matter how we rearrange the terms. So in other words, the commutativity property, which is true of finite sums, holds in these under these conditions. I'm not going to prove this to you, but the proof is pretty much based on the definition of convergence and the fact that there is a limit and so on, and basically on the idea that there is only finitely many values which may be of opposite sign. Okay? However, if we have a sequence which has infinitely many positive and infinitely many negative terms, and assuming that the series associated with the sequence in the given order is convergent, okay, then different rearrangements of terms may in fact converge to different sums or even diverge. So this makes this kind of series very interesting and very unstable. So that's something that we may want to think of as a negative property or a problem with these series. Okay? However, as we're going to see, in particular, alternating series also have a very nice positive good property. Okay, so it's not all bad what is happening to this series. And not only that, but these alternating series do come up in lots of the applications having to do with the main reason why we're looking at series, which we will look at in the next topic. Let me start by giving you a definition, okay? And the definition is as follows. If we start from a positive sequence, okay, then the series obtained by not just adding all the terms, by adding them in with alternating signs, the negative 1 to the power n will produce positive or negative 1 according to whether n is even or odd. And therefore, a series like this will look like, well, if we start at n equal 1, it will look like a negative a1 plus a2 minus a3 plus a4, positive, negative, positive, negative, positive, negative. Or, of course, we can also start with a positive term for the series. In that case, if we use the usual convention of starting the series at 1, the coefficient in front of the an's will be negative 1 to the power n plus 1, so that we start with a positive. In this case, the series will look like a1 minus a2 plus a3 minus a4, positive, negative, positive, negative, positive, negative, like that. So if we have a series that looks like either one of those two, we're going to call this, for obvious reasons, an alternating series. Because alternating series have infinitely many positive and infinitely many negative terms, they actually can produce inconsistent convergence behaviors when their terms are rearranged. So for some alternating series, we may be able to rearrange the terms in such a way as to have a new series which will converge to something else once again or diverge. Again, not all alternating series have this property. We're going to see shortly which ones do. But as I said, there is also a good side to this series, and there is the fact that they have a very nice property. So I'm going to keep you a little bit more in suspense before I tell you what that property is. So let me show you just one example to show you what I mean, and how is it possible that by rearranging these series we can obtain something, whatever it is that we want. Okay, we're going to look at this particular series. Notice that this is pretty much looks like the harmonic series is just something of the form almost 1 over n, except it's not 1 over n, but it's negative 1 to the power n plus 1 over n, which we're going to call the alternating harmonic series. And again, if we write down the first few terms, they look like we start at 1, and then we have minus 1 half plus 1/3, minus 1/4 plus 1/5, and so on and so on and so on. Now, as I'm going to show you in a minute, this series actually converges because it does have that nice property that I told you about, that I've been announcing for a few minutes now. However, it also has the other bad property. Okay, so if we look at the sum of all the positive terms, that will consist of the sum from 1 to infinity of things that look like 1 over an odd number. And if we look at all the sum of the negative terms, this will look like the sum of all the terms which have an even denominator. Both of these series actually diverge to infinity, and that's easy to prove by comparing them with the usual harmonic series. The second one is just which is 1/2 of a regular harmonic series. The other one is not quite 1/2, but again, by a comparison test, you can check that it diverges. What that means is that both of those series actually have infinity as a sum. What this means is that in both of those sums diverge to infinity, which means that both of those sums have an infinite amount of numbers in them, an infinite amount in the sense of by adding them up I can go all the way to infinity. So I have as much number as you want, if you want to put it that way. It's not a very mathematically correct way to do it, but hopefully it will convey the idea. Okay. So now let's say that this thing we want to make it converge to some number L. Okay, this series is going to converge, and we're going to figure out pretty soon what it converges to. But for now, let's say that I want to make it converge to some number L. So let's say I want to make it converge to 10. Okay, so what do I have to do? Remember, I have an infinite amount of positive numbers. Okay, and so I can keep adding them until I get to L and go a little bit beyond. Okay, so what I'm going to do is I'm going to add enough positive terms until the sum is greater than L. Okay, and then what I'm going to do at that point, I'm going to add enough negative terms until the new sum is less than L. Okay, and because I have an infinite amount of an infinite quantity to play with, both with the negatives and the positive, I can play this game as much as I want. On the other hand, both of those sums, the numbers will become smaller and smaller. And so what I'm going to do is I'm going to be hovering around L and go back and forth, above, below, above, below, above, below, until I get to infinity. And in fact, I can repeat this process to infinity and basically just make the whole series converge to L. It's a bit of an artificial process. Notice also that if I do this, the series of course is not going to be alternating anymore, but remember I said the point here, the reason why this has these properties, that it has infinitely many positive and infinitely many negative terms. So this is the problem. Okay, but now let's have a look at what is the good side of alternating series.